house of innovation.
The curved layers generated by our neural slicer are then used to supervise the robotic hardware to complete the 3D printing. There are 3 problems in the existing slicers for multi-axis 3D printing. First of all, they always require volumetric mesh with high quality, which is hard to be generated on models with complex geometry and topology. For the recent work of S-cubic slicer, the optimization is indirectly conducted in the deformed space, but not in the model space. The distortion between 2 spaces may make a region that is self-supported in the deformed space become overhang. Lastly, the nonlinear optimization employed in the previous methods heavily depends on a good initial guess. For example, different initial fields obtained by the heat method with different heat sources will lead to different curved layers by using the S-cubic slicer. Our neural slicer can handle all these challenges. The input of our slicer can be a model in different discrete representations, including a solid model, a shell model, skeletons of struts, or skeleton for tubular solids. Our neural slicer is agnostic to all these different representations. During the pre-processing step of our pipeline, different representations are first converted into an implicit solid. Voxel-based finite element analysis is employed to compute the stress field. After that, a volume mesh caging the input solid is generated as an intermediate representation for numerical computing. The core of our slicer is a neural optimizer, where neural networks are employed to formulate the functions of cotangents and the scaling ratios. These 2 functions are then used to drive the deformation of the caging mesh. As a result, a scalar field can be obtained in the model space by the mapping between the deformed and undeformed cages. The local printing directions are obtained as a gradient of the scalar field. Different loss functions are defined for different manufacturing requirements. As our pipeline is differentiable, backpropagation can be realized to minimize its loss functions. The optimization is conducted iteratively so that a scalar field can be optimized in the model space. After that, we can extract its isocurves on the caging mesh, which are trimmed to obtain the curved layers for printing. Our neural slicer can generate curved layers considering different manufacturing objectives. For example, we first only consider the support-free requirement on the bunny head model. Then the strength reinforcement requirement is added. Their mechanical strength is evaluated by the compression test. 30% increase in the breaking force can be obtained. The region of structure failure is changed from the root of the ear to the hole. Our neural slicer can handle models with very complicated topology, such as the shelf model. The genus number is 30. The curved layers generated by our slicer can align with the stress field very well. The comparison between our neural slicer and the S-cubic slicer is conducted on the bridge model with the requirement of strength reinforcement. Both slicers can successfully generate curved layers. Finite element analysis with anisotropic material properties is conducted to compare the strain distributions. In the 3-point bending test, the result generated by our neural slicer gives a breaking force that's doubled. Now we demonstrate the physical printing process on the spiral fish model. And also the bunny head model.